Alright, number one here, you can see that, you got a sum, you got, negative 0.2 to the nth power, you got 0.6 to the n minus first power. Both of them are something to the nth power, so these are both, these would both be geometric series. The fact that you've got, both of these r values are less than 1 in absolute value means that these are going to be convergent. So what we can do is we can split this up into two separate sums, right? From n equals 1 to infinity, we can do minus 0.2 to the nth power plus the sum from n equals 1 to infinity, 0.6 to the n minus first power. Okay, and let's just write out the first couple terms of what these are, just so we have a very good idea of what's going on. The first, for the first sum, the first term is when n equals 1. When n equals 1, this is the first power. So this would be negative 0.2 plus negative 0.2 squared plus so on. That's the first infinite series there. The second infinite series, the first term, when n equals 1, you would actually have the 0th power here. And anything to the 0th power is 1. So this would actually be 1 plus 0.6 plus 0.6 squared plus. Okay. So both of these are geometric series. They're both going to converge because both of them have r values less than 1 in absolute value. What does the geometric series converge to? It converges to the first term over 1 minus the common ratio, which in this case is negative 0.2. Okay. The other geometric series also converges. It converges to the first term, which is 1, over 1 minus the common ratio, which in this case is 0.6. Okay, so what do we got? We got negative 0.2 over 1.2 plus 1 over 0.4. And if you work out what that is, I get that to be 2 1/3 or 7/3. Okay. We did that by hand. Of course, you could check it with the calculator too. You could check it just simply by typing in the original series. I mean, the only problem is you can't go to infinity, but maybe go from 1 to 50. You could do negative 0.2 to the nth power plus 0.6 to the n minus first power. And the calculator confirms that, yeah, 2 1/3 is in fact the limit. All right, number 2 is most definitely not geometric, right? It's not just something to the kth power or something to the nth power. And in fact, if you look at the individual terms and you look at what happens to the individual terms as k goes to infinity, you notice this is degree 2 over degree 2. So the limit's just going to be the ratio of the leading coefficients, which in this case is 1 over 1. Okay, so as k goes to infinity, the individual terms approach 1. And since that's not 0, the series diverges by the divergence test. Okay, very important to realize the difference between the limit of the sequence with no sigma and this series that does have the sigma. See, this series means you're adding them all up. And basically you're adding up a bunch of fractions that are getting closer and closer to 1. So eventually this looks like, basically, 1 plus 1 plus 1 plus 1 plus 1 forever, which of course just keeps getting bigger and bigger, and that's why the series diverges. Okay. Let's see, for number 3, we can't use the divergence test. Okay, because notice that, if I took a limit as n goes to infinity, then that would be 0. And so, the divergence test fails here. This in itself is not enough to determine whether the series converges or diverges. All we know that we can't use the divergence test to say that the series diverges. Okay, so we got to do something else. And what we're going to do is a little trick that we've seen before, partial fractions. One over n times n plus 1 by the theory of partial fractions is going to be something over n plus something over n plus 1. To figure out what goes above the n, you would cover up the n, plug in n equals 0. You'd have 1 over 1, which is 1. To figure out what goes above here, you could cover up the n plus 1, plug in negative 1. You'd have 1 over negative 1, which is negative 1. Okay, so it turns out that, a sub n, well, let's not do that. Let's write another way to write this series would be to use that partial fraction decomposition like that. Okay. So let's start looking at the partial sums. Okay, let's do s sub 1, for example. S sub 1 is just the sum of the first term, which would be 1 minus a half. That's just plugging in n equals 1 here. Okay. And let me I'll put parentheses around here, so I'll put parentheses around here. Okay. S2 would be the sum of the first two terms. So that's going to be the n equals 1 term plus the n equals 2 term. We'll write out a couple more of those. S3 would be the n equals 1 term plus the n equals 2 term plus the n equals 3 term. Okay, and that's probably enough to see a pattern actually here, because notice that with the with S2 the 1/2's canceled, so that's simplified to just 1 minus a third. With S3 the 1/2's canceled and the 1/3's canceled. We ended up with 1 minus a fourth. Okay, and you can imagine that every single one of those partial sums is going to have that same kind of cancellation. So if we try to see the pattern here, Sn is always going to look like this. And let's see, when n was 3, we had 1 minus 1 over 4. So the general pattern here is going to be 1 minus 1 over n plus 1. Okay, when n was 3, we had a 4. That's why it's n plus 1. Yeah, so what we can do is we can simply take a limit as n goes to infinity of the partial sums, and that's actually doable here because we had that nice cancellation. As n goes to infinity, this fraction here goes to 0, so this looks like 1 minus 0, which is just 1. So it turns out that that series converges to 1.